Okay. Our last presentation this session is from Thomas Grischek on riverbank filtration with siphon wells, breathing new life into an old idea. Thank you.
Hello, everybody. It's a perfect match, I think, because it's an advertising slot now for siphon wells, just before the lunch break, and especially for Harry, because if he's using so much energy for the RO, the siphon system may be one choice, one option. So I would like to mention that the results which I'm presenting are coming from the Aquaness project, and this project is near to completion. So you will find it at the webpage here, aquaness.eu, and this was covering the combination of natural treatment techniques with engineered systems like nanofiltration, ultrafiltration, reverse osmosis, and others. And there was also a work package on bank filtration, and there is a special issue in the Journal of Water with 19 papers covering recent aspects of riverbank filtration. So you see the different combinations here, if you can see it from the back, with even decentralized nanofiltration and other things. And we had 5 demonstration sites, and one what these 5 sites had in common, except the site in India, was that they used old systems for riverbank filtration and having siphon wells. So I would like to come to explain a bit more about siphon systems, about construction, the hydraulic design, and the most important thing, the energy saving, and to conclude. So what's the principle of a siphon? If you are thinking back to your childhood, and if you maybe have been hiking, you go to a hiking tour and you need some fuel, you may ask, or you may not ask, but you may get the fuel from your father's car, and so you have to use the principle of a siphon. And if you go to a large scale, you connect a typical vertical well or whatever, a shaft well or a horizontal well even, to a collector well by just putting a pipe, of course a vacuum-tight pipe, between the 2 wells, or to a collector well, to a collector pipeline, and you place only a pump in the collector well. So you can, of course, then use the best pump you can ever get, and it is not necessarily a submersible pump. And so you don't need a submersible pump for each of your wells, because you connect all the wells to one collector well. Of course, there are some technical issues involved, but it's not a problem, so you can manage. And then if you look in the history, so you see that many people have used that system because they had no submersible pumps during that time, so they had to get the water out with other things. And so only later, when we had these nice engines, we replaced, or we had new wells, not looking on the siphon systems, but having other things like with a stronger drawdown and with better control, of course. It's not, I don't want to say that siphon systems work everywhere, because you are depending on the level of your groundwater below ground. So a good level would be at, say, maximum 12 meters, because you have to dig the pipes, and the wells have to connect it to the pipes and then to the collector well. But we find that many old systems are still running with these siphon systems, and you find it, for example, in one of the oldest ones in Germany at the Düsseldorf site on the River Rhine. So it's from the 1870, and they even constructed a tunnel where they placed the collector pipe, so they could repair if there's any leakage, so they can easily go. You can walk there. Of course, this is quite expensive, so we can do it another way. If we go to my home city, it is Dresden, so we have a siphon system which has been developed step by step. So first they started with siphon pipe 1, so these are old big shaft wells connected to a collector well in the waterworks. Do not see, you don't see the laser. Where you see the waterworks, and there is one black dot, and this is the collector well for all these wells, for all these 72 wells. And if you look from the river towards the waterworks, you just see the caps there from the wells, and you can imagine that if you have a flood, they are fully covered with water, but they still operated, because we have no electricity there, so it's no problem. Of course, you have to seal them properly, but there's no problem with electricity supply. Another case is from the river Mulde. It's a small river, also not far from Dresden, and it's again from 1900. So they constructed shaft wells, connected all these shaft wells to one pipeline, the red one, and it's bringing the water to the waterworks. And the collector well is at the waterworks. So they have a 1.3 kilometer long pipeline getting the water out from the other place. And if you look at it in our days, so we have the green ones, which are still in operation and very well maintained. So it's more than 119 years old. And the yellow ones would need some maintenance, but not much. And few wells are out of operation, the red ones. And if you look at the construction, it's very simple. So it means that even if you start a larger site from scratch, so if you are planning one, you can work, if you go to Africa or if you go to Asia, with some simple wells. That's not necessarily a very unique structure or something like that. So it works well. And you only need this suction pipe. And if you look at the more better equipped sites like the waterworks in Dresden, they are also using bank filtration and managed aquifer recharge like infiltration basins. So you see these blue dots in the middle. These are wells, vertical wells with submersible pumps. And then we have a long row, these are the older ones, the siphon wells. So now we can very nicely compare them concerning energy costs, as we will do in a moment. And this is also true for Poznan in Poland, for Hungary. And Budapest, for example, is the case here, where they use bank filtration wells at the islands. And they have a large number of wells, as you see. And they have a unique feature that they even have small horizontal collector wells, which are connected to a collector shaft. So they're using the horizontal collector wells even as siphon systems. And this also allows to be flood protected, so we can cover the wells. You don't need even a surface structure, so you just see the small dots here, the spots with the concrete, and then they need one collector where they can connect all the others. And so you don't need to protect every well individually. And if you look at the number of wells, so it's very much different. It depends on the hydrogeology, of course. So for example, if you look at the Donau Ried, this is with 40 wells having the same capacity like in Hamburg with 200 wells. So it depends on the hydraulic connectivity, of course, how many wells you need for a certain capacity. But the majority of these old systems need rehabilitation now. And so the people who have been responsible, they are very familiar with the new vertical wells and with submersible pumps, and they propose submersible pump systems because they hesitate to make all these old stuff of calculations and which you don't find. And that's why we have been looking at the old things, and we prepared an Excel spreadsheet to help the engineers to design the siphon systems. So it's just that you apply the old equations and put it in the new feature, and then you can use it in an easy way. So comparing to 3 days that the engineers had to calculate by hand, so now you need less than 1 hour, and you can make a nice combination of the friction loss in the pipes and the valve drawdown of the wells, so you combine both calculation needs. And so we used this, and it's freely available, so you can also download it from the Aquanes website, and it is useful for up to 100 wells with 3 laterals or 3 collector pipes, and you can also find something in the literature that has been validated, so it's just to motivate everybody. If you think about siphons, you don't need to do the nasty maths. You can use it, and you are quite sure that it may work. And this is used, it has been used already for the validation for a real case, where they had to rehabilitate a siphon system here. And so there are, of course, also different technical possibilities to rehabilitate an existing system. And if you compare the results for the friction loss before and after rehabilitation, you see that a few of these pipes were suffering from incrustations, but after rehabilitation, there was much better, much lower roughness in the pipes, and so we had an improvement. And if you compared to the individual discharge from the wells, so we see that most of the wells deliver more water now and some less, but this is just because it's a connected system. So these wells have been delivered more water because the others didn't. So you can apply this tool to see what could happen if you get some significant changes in your system. And but the strongest motivation to talk about siphons is the energy saving. So you know that you have different energy demand for different, let's say, tasks or different processes, and especially we have the friction losses, or pump losses, and the cable losses, and which can be reduced if you apply a siphon system. And we have two case studies, and one is in the German case, where I have shown the large RBF and MAR system in Dresden. So we can compare the blue dots, the siphon wells, with the yellow dots here, with the individually operated wells of submersible pumps. And of course, it's depending on the hydraulics. So in this case, we have to pump the water up to an aeration. And we compared, and we found first that we had energy saving of about 50%. And then the water company said, oh, this cannot be. And then they connected some more siphons, and to make it a bit worse, that is not so drastic. And so we found still then we had 36% savings. And if we go to another side, because it may be only for one side, so if we go to Budapest with the help of our Hungarian colleagues, with Zsuzsanna, and we found that for that case, it's a different hydraulics there, we found even 69% from a real case. So they have the siphon systems and they have other systems. So we can compare directly, and we find that on average, it was about 70% less energy consumption for the siphon systems. And to sum it up, if we come to an average in the table, so we found that the specific energy consumption so it's kilowatt hours per cubic meter pumped water, so it could be about 38% less than for a well which you have a submersible pump. But this is for the new pump, so this is with a high efficiency already. So, but if you take into account that you have the aging of a well, so you have also cable losses, you have also incrustation in your pump, maybe not sufficient maintenance, so it would be even more the difference. To conclude, so we have the demand for rehabilitation for many siphon systems because they are quite old, but it's worth to keep them, to rehabilitate them, and not to replace them by submersible pump-operated wells. And you can also use this siphon tool to check the design. And so I think it's also a contribution to prevent climate change, that you save your energy at your place. And that's what I want to say. Thank you.
Thank you very much, Thomas, and thank you for keeping to time. Let's just take a couple of minutes for any burning questions for the last three speakers. Just a few minutes. Thank you.
Wait for a microphone.
Yeah, just wait for a microphone. We'll take one there. Have you had a question before? So we'll put you second. You've had a question before. Have you had a question before? Yes. Anyone hasn't had a question before? You're number 2. And then we'll go from there back to the next one. And you're number 3. Thank you. Please.
My question to Dr. Edda, on contingency planning, right? So it's good that you address the issue of MAR as a remedy for water supply in cases of, say, nuclear wars, right? So do you select the unconfined aquifer, what you showed in the profile, hydrogeological profile, as a storage of the groundwater mount infiltrated? So, and did you take into account the potential of radioactive fallout and contamination of the site, which is, Vados zone is very, very coarse, right? So therefore, in case of a war, right, so all this mount will be contaminated, right? So why not to go deeper, right? So to the second aquifer, right? So which would be isolated from the radionuclides, right? So was it a factor when the Emiratis are rich? They can afford to use injection wells.
So I don't think that a nuclear war was taken into consideration when the project was planned. It was really more failures of the desalination plants as a driver. The contamination, yeah, of course, that is an issue, and that is why I said at the end that the development of protection zones is on the agenda, so to prohibit certain activities in the wider area. On the other hand, it's quite a remote area, so the risk is rather low because there is not really much going on. But yeah, so nuclear fallout was not considered in the planning of the project. Now, why the shallow aquifer was chosen, it's just for, well, it's easier, of course, to infiltrate in the shallow aquifer. And also, the deeper you go, the more saline the water gets. And in terms of water quality issues, then it's just you know, more easier to use the freshwater lens for such an operation.
Thank you. Dr. Gang Lu is the next.
Thanks, the President, for remembering my name even. I'd like to acknowledge Harry for delivering the talk. Actually, I'd like to deliver my question to all the audience here, because we are really looking for good candidates on using riverbank filtration and Mars for drinking water purpose. And now we are running 2 national and international projects with a fund of about $2 million. And we have a program called PIFI, so it's the President International Fellowship Initiative. So we can offer especially the postdocs, very good opportunity to work on that with a very high, I think it's even higher salary than the postdocs in Netherlands, and working on the topic in China, Netherlands, and the United States. So if you have any good candidate, please help me. Thanks a lot.
Thank you. Perhaps participants can contact you directly for that. Thank you very much.
Great.
And down the front here, please.
I have a question for Harry Timmer about his interesting talk about riverbank filtration and reverse osmosis after that. Harry, how do you deal with the problem when the aquifer passage results in 2 flows, a suboxic and an anoxic flow, and the water you recover is going to provoke well clogging particles, which might clog also the RO membranes?
Thank you, Peter, for this question. We try to avoid that. We like very much the anaerobic system that we have, and if it's mixed with aerobic, I think indeed we will have these kind of troubles. So we like to avoid these problems to make and design these systems as good that we don't get this mix. We hope.
Okay, yeah, hope. Thank you very much. Look, we're a little bit over time. It's never enough time for questions, but if you do have more questions, please go directly to the speakers that you heard from this morning. Thank you to all the 7 speakers in the end for a very interesting session. And thank you to all of you in the room. It's a big crowd for a parallel session, and that represents exactly the importance of MAR in the context of integrated water resource management. We do it, as Bob said, It's a tool to be used. What are the higher objectives we're trying to achieve? Thank you, Alice, for co-chairing and timekeeping. Yes. This session will continue at 3 o'clock here as a flash session, which means short, sharp presentations. We have 7 presentations in 40 minutes, so that'll be a nice challenge. If you're presenting in that session, please make sure that you've loaded your PowerPoint to the guys in the back right-hand corner. Other than that, please enjoy your lunch, and hopefully we'll see you back here at 3 o'clock, and thank you all very much.